In this video, we will discuss three important parameters related to parabolic reflector antennas. They are F by D ratio, what is meant by F by D ratio, spillover, and backlobe radiations. The ratio, spillover, backlobe. So, F by D ratio, spillover, backlobe. F by D ratio, spillover, backlobe. Okay, so let us discussing what is this F by D ratio. What is this? Let's go. So F by D ratio means, for example, this is my parabolic. This is my parabolic reflector. Okay. So this is my primary end. Okay. So the distance from here to here, it is nothing but the focal point. Okay. Okay. So let us take this for example. This is my parabolic reflector. This is my parabolic reflector. Okay. So this is my feed point or source. Okay. So this distance from here to here, from this here to here, we call it as here. Okay, this focal point. And this opening from here to here, we call it as D, diameter of the aperture. D is the diameter of the aperture. Okay. So first let us discuss the first one, F by D ratio. F by D ratio. So, for example, I am taking three cases here. So this is my open end. Okay. So this is case A. This is case B. This is case C. Let us A, B, C. Okay. So what I have done in case A? What I have done in case A? Okay. This is opening of case 1. This is the opening of the case. Okay. So what happened if there are three cases? Where can I keep my feed point? Okay. So the ratio of focal length F to the diameter of a picture is the another. The ratio of focal point and diameter is another important design constant. Another important design constant for getting a pencil beam. Okay, pencil beam means which is used for generating getting high gain. Pencil beam is nothing but it radiates particularly in the direction only. It radiates particularly in that direction only. That is called as pencil beam. That is called as pencil beam. Okay, so here where can I keep my active angle? So one at A, I am keeping my antenna or focal point here. Second point I am keeping on here. The third point I am keeping my feed point outside the directrix. So one is the three possible cases is the first point is focal point inside, that is A, focal point inside the aperture of paraboloid. Aperture of paraboloid. Okay, so this is A. B is, second one is focal point along the plane, of open mouth of paraboloid. Open mouth of paraboloid. So this is B. Coming to the C is focal point beyond the open mouth of paraboloid. Open mouth of parabola. Okay, so these are the three cases. First case, I have kept very inside. Inside, this is my opening. I have kept very inside here. Okay, so this is my F. This is my focal point here. Okay. Second case, so this is my F. And this is my F. Okay, so this is your D. This is your D. Okay. The third point, this is my F. So what happened? What will happen if you keep your focal point inside the aperture of the parabola, right? What will happen if you keep the focal point along the plane of the open mouth of the paraboid? What will happen if you keep the focal point uh, beyond the open mouth? Okay, so among these three configurations, which configuration will give better pencil beam radiation or high gain? Okay, so let us see here. Let us come to the A. Let us come to the A. What is this A? Here the focal point is inside. Okay, so what is the disadvantage here? It is using, it will transmit the signals, it is using only some portion of the reflector. Okay, it is not utilizing. So when the focal point is very small, okay, it is when the focal point is very small, the focal point light inside the open mouth of the paraboloid, it is very difficult to obtain uniform illumination because it is utilizing only this portion for reflection. Okay, it can cover only this portion, only can cover this portion. Okay, so that's why what is the disadvantage here? It is difficult. It is difficult to obtain uniform. It is difficult to obtain uniform illumination. It is difficult to obtain uniform illumination if you take your focal point very nearer into the earth because it is utilizing only this small portion for again retransmission. Okay, next. Let us take the third case. What happens if I keep my focal point beyond or so much long? Okay, so what happens if I keep some of the rays? Some of the rays may go like this. Okay, so if some of the rays may go like this, okay, they are not useful. Okay, if they fall on the reflector, then it will send in this direction. Okay, and if they fall on the reflector, they move in this direction. So what is the disadvantage here? Here, the disadvantage in C is, C type means if you keep your focal point beyond the open mouth of the point is, here we are unable to direct. We are unable to direct. We are unable to direct all radiations from the source to reflector, from the source to reflector. So here, what is the problem here? Here the problem is it is difficult to apply uniform illumination. Here the problem is we are unable to direct all radiations. Okay, some of the rays will get wasted. Okay, but if you take your focal point along the plane of open mouth of paraboloid, this condition will give pencil beam or high gain pencil beam shape pattern. So it is always prefer to keep your focal point along the directrix, along the directrix. Okay, so uh, it is always so. If you have this condition, will use the maximum pencil beam radiation, maximum pencil beam radiation pattern. Okay, so that is nothing but, so see here. So this is one. So here the case one, here the focal point is, for example, this is the open end. Here the focal point is inside the para aperture. Okay. So here the F by D ratio is less than uh, D by 4. Okay. But here it is exactly on the directness. Here F by D is D by 4. So for practical applications, so it is preferred to that F by D should be ratio is equal to 1 by 4. F by D should be equal to 1 by 4. So always the ratio of F by D should be equal to 1 by 4. So for practical applications, the value of focal length to a diameter always lie in between 0.25 and zero point 0.5. So the F by D ratio should be 1 by 4. So 1 by 4. So for practical applications, the value of focal length to diameter ratio lies between 0.25 to 0.5. 0.5. Okay. So these are all the things regarding F by D ratio. F by D ratio. F by D ratio. Okay. Let us discuss spillover. What is meant by spillover? Let us discuss what is meant by spillover. So spillover means for example, this is my parabolic reflector. This is my parabolic reflector. Okay. So this is my primary source. This is my primary source. Okay. So here, okay. So I am transmitting here my signals here. And I transmitted compulsorily the signal should get captured and written back like this. Okay. Written back like this. They all move same direction. Okay. So, but some of the rays, so here, for example, let us consider this ray falls on the reflector, but this is not reflected back. Okay. So here in nature, few radiations originated from, so what is meant by spill out is few radiations, few radiations originated from the primary radiator, from the primary radiator. Okay, so primary radiator are not, practically it is observed that some of the rays are not fully captured by, fully captured by, are not fully captured by a reflector, are not fully captured by a reflector. Such non-captured, such non-captured rays form spillover. Such a non-captured rays form spillover. Such a non-captured rays form spillover. So this is the definition of spillover. Clear? Okay, so not all the rays which are generated from this primary antenna are captured by this reflector. Okay, so such non-captured, so practically it is observed that some of the rays are not fully captured by the reflector. Okay, such non-captured rays are called as spillover. Such non-captured rays are called as spillover. Okay, so let us discuss the third one. What is the third one? That is backflow. Backflow. So next one is backflow. What is meant by this backflow? Okay, so here let us consider this is my parabolic antenna. This is my parabolic. Okay, so this is my, this is my horn antenna. This is my horn antenna. Okay, so generally how the takes place, this is my horn antenna, primary antenna. Okay, so you see here, this is primary antenna. It will generate, it will falls on the reflector and comes like this. This ray also falls on the reflector and comes like this. And similarly, this ray also falls here and comes like this. Okay, so this ray also falls here and comes like this. Okay, but so this is our primary antenna. You should radiate only in this direction. Okay, but what happen is some of the rays. So here not only radiate in this direction, but it will radiate some back lobe radiations like this. Okay, but as you are seeing this, these are unwanted rays which are generated by this primary. These are unwanted rays that are generated. You should radiate only in this direction. Should radiate only in this direction, but it has radiated some of the rays like this. Okay, which are unwanted rays. But as you are seeing here, these rays are getting mixed with this original rays. Okay, so in addition to this, okay, so few radiations originated from primary radiator are absorbed in forward direction. Okay, such radiations get are added with desired parallel. So this is called as, so see here, these are back lobe radiations. These are also getting added with desired parallel beams. Okay, so this is called as back lobe radiation. This is called as back lobe radiation. So what is the definition? Few radiations. What is meant by this back lobe radiation? Few radiations originated from primary radiator are absorbed in forward direction forward directions, such radiations get added with desired parallel beam. Desired parallel beam. So this type of radiations are called as, okay, so this is called as back loop radiations, as it originates from the back loop of primary radiator, as it originates from the back loop of primary radiator. Obviously, this back lobe radiations are unwanted. Okay, and they considerably affect the reflected beam, and they continuously affect the reflected beam. Okay, reflected beam. Okay, so reflector.